Okay, can everybody see my screen that says osmotic pressure? I just want to double check before I start talking here. Great, thanks, Sierra. All right, perfect. Well, let's talk about osmosis. I've heard students say, I'll just show up to class and fall asleep, and maybe I'll learn something through osmosis. Okay, because this is the movement of particles from a region of low concentration to a region of high concentration. In fact, that's the definition of what osmosis is. It's the movement of solvent particles. So no movement of solute particles. So movement of solvent particles only from a region of low concentration to high concentration, which might be counterintuitive. And they're moving through a semi-permeable membrane. So obviously this membrane is permeable. When it says semi, it means partly permeable. It's permeable to solvent, isn't it? But it's not permeable to solute. Okay, so not permeable to solute. Okay, and the solvent is always going to go from a more dilute solution to a more concentrated one. Now that might be counterintuitive, but the way that I think about it is like this. If I have two solutions separated by a semi-permeable membrane, they're going to want to do whatever they can do to be more like each other, right? If you have one that's more concentrated, one that's less concentrated. Well, if the particles can't move, if the solute particles can't move and only the solvent can move, what's the only possibility? Is that the solvent is going to have to go from the more concentrated to from the less concentrated to the more concentrated to try and dilute it, right? If solvent went from the more concentrated to the less concentrated, that would just make the more concentrated one even more concentrated. So that's completely the opposite of what osmosis is. And we're going to define what osmotic pressure is. Okay, so osmotic pressure is the pressure that's required to prevent the net flow of solvent. So you've got your solvent going from your concentration of from your region of lower concentration to higher concentration. Well, how do I stop that solvent from moving? Well, you can stop it by putting pressure on it. And the amount of pressure that can be applied, it can be calculated using this formula here. Pi is equal to mRT. Now, you might be wondering, if it's pressure, why don't they use P? Well, the capital letter P, pressure in chemistry, that's used for gases. So when we use the Greek letter, the capital P in Greek, which is the capital Pi that you see here, this is osmotic pressure. So osmotic pressure. And osmotic pressure is measured in atmospheres. So we're still going to measure it in atmospheres. And it is equal to the molarity of the solution multiplied by the gas constant R multiplied by the temperature in Kelvin. If you think about the units of molarity, which are moles per liter, and then we have the gas constant units, liter atmospheres per mole Kelvin, and then we have the temperature in Kelvin. Well, if you look at the units, moles cancel, as do liters and Kelvin, and you're left over with atmospheres. And so that's how we calculate osmotic pressure. If after what I just said to you, you're still like, I'm not quite sure what you mean by osmotic pressure, Mr. Deon. I'm not even sure if I know what you mean by osmosis. Well, a picture is worth 1,000 words. So let's say we have a solution in a pure solvent in a U-tube. This is called a U-tube. Hey, it sounds like YouTube, the channel, right? No, this is actually called a U, capital letter tube, not Y-O-U tube. So a U-tube, and we have a semi-permeable membrane down here at the bottom. Okay, so what does that mean? It means that it's permeable to solvent, right? But it's not permeable to the particles that are in the solution. Okay, so if you look at any of these three blow-up diagrams here that show the movement of particles, you'll notice that none of the arrows are on the solute particles. The arrows are only on the blue particles, which represent the solvent. Well, what was the definition of osmosis? It was the flow of solvent particles from a region of low concentration, right? This is low concentration to a region of higher concentration, right? Because if you have a solution, well, obviously that's got a higher concentration of solute particles than the pure solvent, which has no solute particles. Okay, so again, they're going to they want to be more like each other. So what's the only possibility? They're never going to be identical, are they? But what we're going to do is we're going to see that the solvent particles are going to move into that solution, okay? and it's actually going to resist the atmospheric pressure, right? Because you're like, well, here it's higher than here. Yeah, it is, okay? But it's because of that flow, okay? It's because of osmosis that it's going to enable the height of this solution to be higher than the height of the pure solvent. Now, the pressure associated with that, like the air pressure that it's resisting, we call that the osmotic pressure, okay? Another way to define that osmotic pressure is if we try to balance it out, right? If you start applying pressure here with, say, a piston or something, and you push it back down to this level so that, or whatever, so that everything's equal as is shown here, okay? The amount of pressure that you applied there is equal to the osmotic pressure. Okay, now if we look at the three, I just dropped my Apple Pencil. If you look at the three kind of blow-ups here, we have the semi-permeable membrane. Here, this is the membrane, okay? When they're at equilibrium, or sorry, in A, they're not in equilibrium, right? You have the pure solvent and you have the solution. So you're going to have more, you know, a greater flow of solvent particles going into the solution, okay? And then once the height of the solution gets to a certain height, and you can see how it's more dilute now, okay? It's going to reach a height where an equilibrium is going to be established, and then the rate of the solvent particles moving either way across the membrane is going to be equal, right? And that's equal to the osmotic pressure, right? This difference in height here is related to the atmospheric pressure, and that is the osmotic pressure, okay? That's one way of measuring osmotic pressure. But then if we were to push it down so that everything's equal, so that we get our rate in and our rate out are equal again, we could also define that as the osmotic pressure, okay? Now, before we look at a problem that involves determining or using the formula for osmotic pressure, right? Pi is equal to mRT, okay? I want to show you what, you know, the red blood cell looks like and how it can be affected by osmotic pressure, right? Here's a normal red blood cell right here. So this is normal, okay? And it says that it's in what's called an isotonic solution. So that's this situation right here. What that means is that the concentration of ions or particles inside the red blood cell is identical to the concentration of ions or particles outside, right? In the bloodstream. Okay. Well, that means the red blood cell is going to have a normal shape. Kind of looks like a donut, okay? But when we put it in a hypotonic solution, what the heck's a hypotonic solution? Well, a hypotonic solution is going to be one where the surrounding environment has a lower concentration of solute particles. So what's that going to do? Since the red blood cell has a higher concentration of solute particles, and it is a semi-permeable membrane, the cell wall is a semi-permeable membrane, what's that going to do? That's going to cause solvent particles to flow in like this, and that can even cause the red blood cell to burst. So it can burst, and it's showing here like it's blown up, right? You see how the donut hole is gone, right? It's getting too big. Now, a hypertonic solution, you can probably guess where I'm going with this. That's where the concentration of solute is high, right? So what's that going to do? That's going to cause the water to leave the red blood cell, okay? And then this is called crenation, right? This is called hemolysis when it bursts. Where did I write bursting? Anyhow, hemolysis, okay? Anyhow, just kind of an interesting application of osmotic pressure and the shape of a red blood cell. Well, let's look at a problem that deals with osmotic pressure. And this problem is titled Determining Molar Mass from Osmotic Pressure. In fact, this is a very good way to determine the molar mass of proteins, which have really large molar masses, compared to using something like freezing point depression or boiling point elevation. It says we have 21.5 milligrams of a protein. It's a non-electrolyte, so there's just that one particle of the big protein. It's dissolved in water to make 1.5 milliliters of a solution at 5 degrees Celsius. The osmotic pressure of the solution is 3.61 torr. We'll have to convert that to atmospheres, huh? What is the molar mass of the protein? Well, remember that molar mass, so if we want the molar mass of our protein is going to be equal to the number of moles divided by, sorry, reading something else and thinking something else. So it's the number of grams per mole. Right, well, we already have the number of grams of the protein. So what we need to calculate is the number of moles of the protein, don't we? Well, what else do we know about our protein, right? We know that we have a 1.5 milliliter solution, and we have our temperature, and we have our pressure. Well, if I have the volume of the solution, and I'm able to calculate the molarity from pi is equal to mRT, right? If I have the molarity and the volume, I can calculate the number of moles, can't I? Right? Because molarity is equal to the number of moles per liter, right? So all I have to do is solve for the number of moles. Take the molarity and multiply it by the volume. Let me show you how you would do that. First, let's start by writing out our formula. Pi is equal to m times r times t. Well, we're given our atmospheric pressure in torr, so I'm going to convert that into atmospheres. I know 3.61 torr, and I know that in 1 atmosphere, I have 760 torr. And so torrs cancel out, and I get my pressure in atmospheres, and it's 0.00475 atmospheres. Now I'm going to rearrange this formula, and I'm going to solve for my molarity, right? Because I have my pressure, I know the gas constant, and I have the temperature. So let's solve for that. Molarity is going to be equal to osmotic pressure divided by gas constant times temperature, which equals 0.00475 atmospheres divided by the gas constant, 0.08206 liters atmospheres per mole Kelvin. My temperature, 5 degrees Celsius. I just add 273 to that, so that's 278 Kelvin. 278 Kelvin, like that. And let's see, atmospheres cancel, as do Kelvin, and I end up with moles per liter, right? Liters per mole in my denominator is equal to moles per liter. So I get that my molarity is equal to 2.08 times 10 to the negative 4 moles per liter. Now I want to figure out the number of moles of my protein, right? All I have to do is take the number, or sorry, the concentration, 2.08 times 10 to the negative 4 molar, moles per liter, and multiply it by the volume. 1.50 milliliters. Can you divide that by 1,000 in your head? If you can't, you could just write it out like this, 1.50 times 10 to the negative 3 liters, right? Because there are 1,000 milliliters in a liter. There we go. And that's going to give us the number of moles of our protein, which is 3.12 times 10 to the negative 7 moles. There we go. So the last thing we want to do is figure out our molar mass, which is equal to the number of grams per mole. Well, I have 21.5 milligrams. They can't give us anything in a normal unit here, can they? In 21.5 milligrams, well, I know that I have, in 1,000 milligrams, I have 1 gram. So I'm going to do the conversion in the numerator. Milligrams cancel out. If you want to just do it as mental math and say, well, it's 0.0215 grams, that works too. Divide by the number of moles, 3.12 times 10 to the negative 7 moles. Let me grab my calculator. Divide by 3.12 times 10 to the negative 7. I'm just checking my work because I did it earlier, but I did it really quickly. And put it in scientific notation because I'm only going to have 3 sig figs. You end up with 6.89 times 10 to the 4 grams per mole. Okay, and if you're like, well, come on, man, that's a gigantic molar mass. Where does that come from? Well, proteins are big molecules, right? A protein having a molar mass, like this is not uncommon because proteins are so big. Okay, very, very big molecule. All right. And here's the solution. as is found in our textbook. So her sanitized view of everything. All right. Anyhow, so let's talk a little bit more about electrolytes. If you remember our last lecture, we talked about electrolytes, remember? And I put up the slide with the light bulbs, and I said, well, if you have an electrolyte, it allows the movement of ions and electrons through a solution, which causes, which allows a current to be passed through an electrolytic solution, whereas you have a non-electrolyte, no current will pass. And if you have a weak electrolyte, you get some current passing, and so you have a dim light bulb. Well, remember, we talked about this before. We said a strong electrolyte is going to dissociate completely. Okay, complete dissociation. An example, let me just give you one off the top of my head. Sodium chloride, right? Easiest example there is. If I put sodium chloride in water, that's going to completely dissociate into sodium ions and chloride ions, right? So sodium chloride solid. All right, complete dissociation, right? That's why I put the arrow in one direction like that. So it says here, each mole of solute gives more than 1 mole of dissolved particles. Now, this statement gives students trouble sometimes. Okay, each mole of solute gives more than 1 mole of dissolved particles. Right? If I take sodium chloride, it's a solid, man. Right? It's just all together. It's aggregated in the crystal lattice. But what happens when I take that one formula unit of sodium chloride and I convert it into ions? Now I don't have one formula unit, I've got 2 ions. So I go from 1 particle, and I know it's not a particle, it's a formula unit, but I go from 1 thing to 2 things, right? So I'm increasing the number of particles, right? That's the whole point of colligative properties, right? It's based on the number of particles, not the identity of those particles. Things like freezing point depression, boiling point elevation, so on and so forth, osmotic pressure as well. So the formula of the compound is going to indicate the expected number of particles in solution. That means that you've got to be Johnny on the spot when it comes to identifying, hey, is this an electrolyte? Is this actually going to break apart into ions? Or is this just a molecular compound? It's non-electrolyte, right? So that's why I showed you sodium chloride is going to give you 2 moles of dissolved ions. Let me give you another example, okay? And I'm probably already teaching you things that we're going to look at in a second. But let's say we looked at, I don't know, let's pick something a little bit different. Let's pick calcium chloride, calcium bromide, CaBr2 solid, right? If I take 1 formula unit of calcium bromide, how many particles am I going to have in my solution? I'm going to have a calcium 2+ ion, but I'm going to have 2 bromide ions, right? So I go from 1 formula unit to having 3 particles, okay? And the number of particles, right, has to be taken into account. So the last point says the Van't Hoff factor takes into account the dissociation of a strong electrolyte to predict the effect on solution. So the number of particles here, whether it's a 3 or whether it's a 2 or whether it's a 1, we call that I. It's the total number of particles coming from a solute. So again, I'm really repeating myself, but you need to be able to judge, like, how many particles am I going to have? Okay, so if it's an ionic compound, just look at the number of ions, right? For example, sodium chloride, ionic compound, made of 1 cation and 1 anion. So it's got a Van't Hoff factor of 2. Calcium bromide, it's an ionic compound made from 1 cation, 2 anions. It's got a Van't Hoff factor of 3. Now, this next slide shows, anyhow, so we have to consider the Van't Hoff factor, or the number of particles, whenever we use any of these formulas. If I'm calculating, vapor pressure lowering, delta P, boiling point elevation, freezing point depression, and osmotic pressure, remember, and if you're like, well, come on, before we didn't stick the I in there, how come we didn't have I in the problem that we just looked at 5 minutes ago or 3 minutes ago? The reason we didn't count I is because we looked at a protein and it said it was a non-electrolyte. If it's a non-electrolyte, so let me just make it simple then. Non-electrolytes, electrolytes, I is going to be equal to 1. Okay, so we didn't even include it, right? But remember that colligative properties, this goes way back to the beginning of our lecture. I said they were affected by what? The number of particles in the solution, not the identity of those particles, right? And if you're like, why is the number of particles important? Well, think about it. We spent quite a bit of time talking about these 3 concepts in the last class and explaining, why is vapor pressure lowered? Remember, at the surface of the liquid, we said, well, the particles are going to block the liquid from, being converted from a liquid to a gas, right? So the more particles you have, the more the vapor pressure is going to be lowered. What about the boiling point elevation? The same kind of rationale. We said, Well, in order for a liquid to boil, that means the particles at the surface have to have enough kinetic energy, and then they escape from the liquid to the gas phase. If I have more particles at the surface, right, that's going to prevent the molecules or particles from being converted from a liquid to a gas. Same rationale. In freezing point depression, come on, think about it. If you have water, for example, and you want to freeze it, okay, the more particles that you have in there, the more it's going to prevent the water from forming its crystal lattice, right? So this is why the Van Hoff factor has to be considered for all four of these, formulas that we've already looked at in this class. Now, here we have no, sorry, we still don't have a problem. I'm really all over here with the slides, aren't I? Anyhow, this one here is more of a conceptual slide. I won't ask you about this on the final exam, so don't turn me off, okay? I want you to understand what the hell is going on. It's very important that you understand chemistry, right? I'll be the first person to admit, and this is one of the last days of school, but I'll be the first person to admit that chemistry, if you try to memorize your way through chemistry, and I'll be honest, you can memorize your way through some of it, right? You can just kind of become a machine that plugs numbers into a formula and just, you're good at using your calculator, you don't make mistakes, and you can probably power through that way, but it's no fun. Not a lot of fun, right? The more you understand, think about any subject you've ever studied in your life, something that you've really loved, something you're just like, man, that class was a lot of fun. It was something that you understood, right? In order for there to be joy in learning, there has to be some level of understanding. So again, don't turn me off. Just bear with me here for a second. Let's say we have iron 3 chloride, right? How many particles would there be when I dissolve iron 3 chloride in solution? Well, I'm just going to write it here simplified. You'd have an iron 3 plus ion, plus you'd have 3 chloride ions. So you think, okay, well, my Van Hoff factor would be a total of, 1 plus 2, 3, 4. I'd have an I equal to 4. So that's expected, but what we see is that it's actually 3.4. It's actually lower than that. Now, if you're like, well, crap, Mr. Deon, what am I going to put in my questions? You're just going to go with the expected, okay? You're not going to worry about observed. This is just a point I'm trying to make here. What about sodium chloride? We said that it was 2. What you see is that it's actually 1.9. It's a little bit lower, right? Glucose doesn't change because it's a non-electrolyte. HCl, strong acid, right? You think you'd get a proton plus a chloride, right? It should have a Van Hoff factor of 2, but it's actually a little bit lower. What's the point? Okay, why are all the Van Hoff factors, except for that of glucose, which is a non-electrolyte, why are they all a little bit lower? The answer is right here. Okay, think about it. If you have an ion in solution, like an iron ion, okay, Fe3+, for example, well, it's not going to be completely surrounded by water, is it? Not all the time, right? Some of those ions are going to be near chlorides. Well, ions in solution may remain clustered near ions of the opposite charge, right? Creating an ionic atmosphere. So the ions do not act independently, and the effective concentration of the dissolved particles is less than expected. That's a fancy way of saying that, look, if I have a cation in solution, some of them are probably going to interact with anions, aren't they? And I bet you there's people who are hearing the sound of my voice who are like, you know what, Mr. Deon, I thought that the whole semester. I was like, if you dissolve sodium chloride, how can every single particle be separated, right? Isn't there a chance that 2 of them might meet each other somewhere? And the answer is yeah. Yeah, it's going to happen, okay? So what that's going to do is it's going to have an effect that it's going to mean like the concentration of dissolved particles is going to be a little bit less, okay? Because not all of those particles are completely solvated. Some of them are just interacting with ions of an opposite charge. Give me a thumbs up, even if you're with me like halfway on that concept. Even if you're with me halfway, you're like, yeah, I kind of understand what you're saying. I might not be willing to jump off a cliff, with it yet, but good. Okay, as long as you're with me, part of the way, you're like, yeah, I kind of see what you're going at here. Okay, but look, this is a good problem. It's a really good problem. This is kind of a conceptual problem. If you understand colligative properties, you should be able to solve this problem, no math. Okay, even though there's a bunch of numbers in here. Okay, look, it says which one would be a better substance or solution to use to de-ice roadways? If you have a 0.1 molal solution of sodium chloride, pure water, a 0.1 molal solution of ammonia, or a 0.1 molal solution of magnesium chloride. Well, if we're trying to de-ice a roadway, what are we trying to do? We're trying to get the ice to melt, aren't we? Therefore, we're looking at freezing point depression, right? Delta TF, which is going to be equal to KF times little m. That's the formula we looked at last class, right? But now we're adding a dimension to it. We're going to have to multiply it by what? The Van't Hoff factor. Okay, we know that pure water freezes at 0 degrees Celsius, right? So it has a freezing point of 0 degrees Celsius. So not much to know there. But what if I had a 0.1 mole solution of sodium chloride? Let's start with that. So if we have sodium chloride, okay, 0.1 mole solution. Okay, so we'll put 4 sodium chloride. Our delta TF is going to be equal to the Van't Hoff factor multiplied by our freezing point depression constant multiplied by our molality. Who could tell me what the Van't Hoff factor I is for sodium chloride? And we already looked at it. Yes, thanks, Sierra. Thanks, Blake. Yeah, the answer is 2, right? I equals 2. So that means our delta TF is going to be 2 times the freezing point depression of water, which is 1.36 degrees Celsius per mole. We looked at that in the last class. Multiplied by the molality, 0.100 mole, like that. Excuse me. Molality cancels, and we get our delta TF, not our TF. It's not our freezing point, but the change in our freezing point is going to be 0.272 degrees Celsius. That means that the freezing point of water would be 0.272 degrees Celsius less than 0 degrees Celsius. That means that your freezing point is going to be negative 0.272 degrees Celsius. Okay. What about for ammonia? Okay, for ammonia. Okay, well, ammonia is a non-electrolyte, right? If I take ammonia in the gaseous phase and I put it in water, I'm just going to get aqueous ammonia. It's not ionic, right? So my Van't Hoff factor is going to be 1. Okay, so now I can speed up the process a little bit. Look, my delta TF is going to be equal to 1 times 1.36 degrees Celsius per mole multiplied by 0.100 mole. Okay, and I get that my delta TF, this one you could do in your head, is equal to 0.136 degrees Celsius. Therefore, my freezing point of water is going to be negative 0.136 degrees Celsius. Okay, so far sodium chloride is looking the best, isn't it? But you know that's not the answer, is it? Right? You know that for magnesium chloride, MgCl2, right, that's going to dissolve in water to give you 1 magnesium 2+ ion, but 2 chlorides, isn't it? Yeah. So that means that your Van't Hoff factor is going to be 3. So you see where I'm going, right? You see that your delta TF is going to be equal to 3 times 1.36 degrees Celsius per mole times 0.100 mole. That means that our delta TF is going to be equal to 0.408 degrees Celsius. That means the freezing point of that solution is going to be negative 0.408 degrees Celsius. So the answer is the magnesium chloride. It's going to be the best. So the answer is, you know, if you saw this question on an exam, the answer is the one with the highest I. That's the answer to the whole problem. The one with the greatest Van't Hoff factor. Right? You know it's not going to be pure water. You know that as long as you dissolve something in water, it's going to have a lower freezing point, right? Well, sodium chloride is commonly put on roads, especially where I grew up in Canada. They put salt on roads all the time. That's why everybody in Canada has a rusty car. I went on my honeymoon in New Mexico, long time, 8 years ago with my wife. It's my first time in New Mexico, my first time that far south in the States. And, you know, we were poor on our honeymoon, had no money, and we spent a lot of time just walking around and enjoying each other's company. And I remember all the vintage cars, all the old trucks that I saw down in New Mexico, and I was like, wow, this is pretty cool. And the reason why there's so many is because they survive. They don't get destroyed by the sodium chloride, right? But I can tell you right now that in Canada, when it gets really, really cold, okay, I mean super duper cold, and they want to break the bank and they want people falling off the roads, in that case, they will put calcium chloride on the roads. It costs more money, you know, more money than sodium chloride, but when the temperature dips enough, sodium chloride doesn't cut the mustard. It won't melt the ice on the road, and so they have to put calcium chloride on, you know, bridges and things like that. Also, another benefit of calcium chloride is that it doesn't chew up the concrete the same way that sodium chloride does. All right, give me a thumbs up if you follow me on Van Hoff factor. You're like, Mr. Deon, I am rock solid on the Van Hoff factor. I know what it means. You know, just point me in the right direction. Point me towards the question, Mr. Deon, and I will nail it. Okay, good. All right.